We want to use the shortcut rules that we've been developing to find the derivatives. And I know I haven't given a whole lot of explanation about how to go about finding those shortcut rules. In previous videos, we actually went and found the derivative of sine function, and you saw how long it took us to do that. In previous videos, we've also found derivatives of functions with x to a power in them. So you can go back and look at those and kind of see how this power rule comes about. But for right now, we're just going to utilize the power rule and the derivative of sine, derivative of cosine, derivative of e to the x, derivative of a natural log of x at will. So let's find the derivatives. We have our functions written here. So the derivative of f is going to be determined by the power rule. So we take the 6 out front and then x to the 5th power. So the derivative of f is 6x to the 5th power. Notice how quickly we found that. It does not take very long once I have the power rule to do this. If I had to utilize the definition, it would take me a really, really long time because at some point I'd have to take x plus h to the 6th power. With the g of x, g prime is negative sine of x. If cosine has a derivative of negative sine. So cosine has a derivative of negative sine. So the derivative of g prime is negative sine x. H of x is a little bit tricky because we have a negative, but don't be thrown off by that. The power rule still works no matter what exponent we have. So we take the negative 5 out front. Notice we have to take the negative 5 out front. And then when you subtract 1 from the exponent, negative 5 minus 1 is going to be a negative 6. That is something oftentimes people will get wrong because they are so used to doing positive exponents that when they get to negative exponents, they'll subtract and they'll do a minus 5 minus 1 and they'll call it minus 4. But minus 5 minus 1 is obviously minus 6. I want to make sure you do understand a little bit about the power rule, how it works out, and also why it exists. So I'm going to go through the definition. You don't have to write this down, but I want you to get an understanding of where the power rule is coming from. And I'm going to do it using this x to the 6th example. So let's say I wanted to find the general derivative of f prime of x. If I had the definition, then what I would have to do is I'd have to say, well, let's plug in x plus h into my function minus f of x into my function, divided by h, take the limit as that thing as h goes to 0 of that. Again, you don't have to write this down if you don't want, but I want to at least show you where the rule comes from. So if I'm plugging in x plus h into the function, and then plugging in x into the function, I have to take x plus h to the 6th minus x to the 6th. And this is a little bit daunting, taking x plus h to the 6th. So I'm just going to go ahead and compute that on my own. If I plug in x plus h to the 6th power, I end up, when you expand that, getting x to the 6th plus 6x to the 5th times h to the 1st. And then you get plus 15x to the 4th times h squared. And then you get a 20 x to the third times h to the third. And then you get back a 15 x to the second, h to the fourth, and then you get back a 6 x to the first, h to the fifth, and then you get back an h to the sixth. Now you're doing all of that and then subtracting x to the sixth. That's such a big expression that it goes off my page. So what I'm going to do, let me make this one a little bit smaller in size. So x to the sixth plus 6x to the fifth h plus 15x to the fourth h squared plus 20x to the third h to the third plus 15x squared h to the fourth plus 6x h to the fifth plus h to the sixth minus x to the sixth. So we see that the x to the sixth and the minus x to the sixth will cancel each other out. Notice every other term has an h in it. So at this point, I can just simply divide by h. And if I divide by h, I get 6x to the fifth plus 15x to the fourth h to the first. I just lower this exponent by 1 on h. Plus 20x to the third h squared plus 15x squared h to the third plus 6x h to the fourth plus h to the fifth. Now, this is an expression that I can plug in 0 into. And if I plug in 0 in for h, because remember we're talking about the limit as h goes to 0. If I plug in 0 for h now, notice that all of these other terms are all of a sudden going to go to 0. And so the only term I'm left with is the 6x to the fifth power. So that's my derivative of x to the sixth. In general, this is always going to be the way this works out. If you take x plus h to a power, the first two terms are going to be x to the power, and then the second term is going to be that power times x to a lower power times h. All of the other terms are going to have h to a higher power. So eventually, they're all going to end up giving you a 0. And we'll just end up with this second term. And so the power rule is a consequence of this second term always having to be the power times x to 1 less than a power. Now, I should say that that's the power that works every time we have a whole number exponent. So every time x is raised to a whole number like 5 or 6 or 7 or 8, then that works. It turns out it works as well when x is raised to a negative power. It is more algebraic work when you do that, though. Now we can see why the power rule works out.